All right, we ready to roll? Yep. Guys, excited? So excited. Another evening edition of 15-18-213? 15-5-13? All right. The memory hierarchy. Yeah. Okay. We know that memory is byte-oriented. We've talked about this before, right? When you think about a memory address, right? Address 0, address 1, address 2, address 3, address 4, address 4 million. What we're talking about is the address of a particular byte. Okay? If we talk about address of an object, we're talking about the address of the first byte of that object. We've talked about memory addressing modes. This is a nice picture to talk about. Right? We have the ALU, the brain of the processor. Okay? And associated with the ALU is the register file, right? Our registers. And remember, the registers operate at the same speed of the processor. Okay, so there's no delay when we're accessing a register. But if we want to access memory, right, we have to load that right? Via move instruction. Or maybe some instructions that allow us to directly address memory. And so what happens is we've got to get that value from all the way over here. It has to cross the I/O bridge, right? The bus, and come to the ALU. So in some architectures, they're purely load store architectures. What that means is that you have to load from memory into a register, and all of your actual useful operations occur only on registers. Okay? And that's the basic model for the x86 architecture. Although, as you guys know, there are certain instructions in x86 where you can reference one register and one memory operand. None allow you to access two memory operands at the same time. At best, it's one. Okay? So what do we mean when we say I/O bridge, memory bus, bus interface? Okay. So when we talk about a bus, we're talking about the system bus or the memory bus. What we're talking about is a really high speed, really low latency, really reliable network. That's what a bus is. A bus is a really high, high speed, that is to say, high number of bits per second, high throughput network that's very low latency. That is to say, the round trips don't take much time. Okay, and it's very, very reliable. Okay, if we think about your Comcast or Verizon at home, right, those are relatively slow. Right, relatively few, gigabits per second. Right. They're relatively unreliable. Packets get dropped sometimes. You're watching, Netflix or, Vudu or Hulu or something, YouTube, right? And things sort of stutter. Okay? Or parts of a section don't come in clearly. All right? And there's a relatively long round trip time, right? Who's Skype with somebody like in India or China? Do you notice that? Yeah. So despite the bandwidth that's sufficient to watch YouTube, the round trip time, that latency still takes a while. Do you see the difference? The bandwidth is how many bits per second we can get, and the latency is sort of how long it takes. It's actually one of the things I think is most interesting about networks. One of the limitations I think people really don't pay a lot of attention to. If we talk about bits per second, that's sort of like how many lanes there are on the highway. Right? The more lanes you have, the more cars you can move per second, right? Is what? Ping time. Ping time is measured latency, exactly right. Because you send a request and you get a reply, and you measure between that request and that reply. So if you just think about it for a minute, right? If you build more lanes, the cars can go at the same speed, right? But you're still getting more cars per second. But if the speed limit is the same, right? It doesn't matter how many lanes you build, it's still going to take just as long to start out at point A, get to point B, and come back to point A, right? And one of the things I think people don't really appreciate is the speed of light is not getting any faster. Right? We can make a huge amount of progress increasing bandwidth, increasing our throughput, our bits per second. Right? More parallelism. We can make a lot of progress decreasing the error rate in those connections where we have errors. But we're not going to make a whole lot of progress improving the speed of light. And so India is really not getting any closer. Right? Beijing is really not getting any closer. The speed of light is the speed of light. Maybe we drill through the center of the Earth, I don't know. But unless there is some huge dramatic change in our understanding of science, the latency to India is going to be about what it is. Okay? So when you look at a computer, you're looking at a network that's like this big. Right? So it can be very, very low latency. Light doesn't need to travel very far, right? Or electromagnetic energy more generally. Okay, so when we talk about a bus, we're talking about a high throughput, low latency, highly reliable network. So basically, for all intents and purposes, we imagine that errors don't exist. And in many cases, we imagine that there's plenty of throughput. Although sometimes we can actually run into situations where there's a little bit of a logjam. So when the ALU, when you use some instruction, right, like a move, that references memory, the ALU has to present ultimately present that address to a memory controller. The memory controller is going to send that address over a system bus to a memory controller, and then a memory controller is going to dispatch the request to the memory itself. The memory is then going to respond to the memory controller. The memory controller is then going to send it over the bus back to the processor. Okay? And that's what this thing shows. The system bus, meaning the bus between the processor and the memory controller, and then the memory bus between the memory controller and the actual memory. So this says that a bus is a collection of parallel wires that carry address, data, and control signals. And that's a true statement. Okay. So here's that picture, right? Where basically we start out with the ALU. Where's the beginning of my picture? Okay, there we go. CPU places address A on the memory bus. So the CPU basically places the address A here, and it travels across the system bus to the memory bus. Okay? The main memory now responds. It's now in a register because we're moving from some address to the register. And now the ALU has it and can use it. The building block of memory falls into one of two categories: DRAM or SRAM. Dynamic RAM or static RAM. RAM stands for random access memory. Right? What does that mean? That means we can access any address we want. Random access. As opposed to, for example, sequential access. Address 0, address 1, address 2, address 3, address 4, address 5, address 6. If you think about old music CDs, those were sequential access. There was one track. Okay? And you had to seek along that track. If anybody here happens to be a big fan of vinyl, right? Vinyl is effectively, sequential access. You put the needle down, and then it goes around and around and around, right? You can sort of guess where you're going to put it, I guess. But basically, it plays linearly. Okay? Now, if we look at our system's main memory, it's composed of something called DRAM, or dynamic RAM. Dynamic RAM basically stores values, ones or zeros, in a capacitor, meaning as stored charge. Okay? The problem with DRAM, or one problem with DRAM, is the stored charge leaks out over time. And so it needs to be refreshed. Okay? And so DRAM needs to be refreshed every 10 to 100 milliseconds. This isn't something the processor does. It's not something you see in assembly. It's something that's handled by the memory system. So the memory causes itself to refresh, but it's something it does that takes time. Okay? DRAM is great because it's relatively cheap and because it's random access. And look, it's relatively fast. But it's way slower than a processor. Way slower than a processor. Which means that registers are way faster than it, right? Because registers operate at the same speed as the processor. SRAM, static RAM, is much faster than DRAM, but still slower than a processor. Okay? It uses a different technology. It's slightly more complicated. Each cell stores a bit with a 4-6 transistor circuit. The good thing about static RAM, or at least a good thing about static RAM, is that it's stable. As long as it has power, it's going to maintain a value. You take power away, it's going to forget. But as long as it has power, it's going to retain that value. So it doesn't require the refresh cycles that DRAM does. Yes?
Is memory inherently slower than a processor because it hasn't been developed as much, or is there something innate to it that makes it slower?
That's an interesting question. Is memory inherently slower than a processor for any reason in particular? So the answer is no, because the register file, for example, operates at the same speed as the processor. The problem is to do that is very expensive in terms of real estate. Remember we talked about the fact that a processor has to be yay big, because if a processor gets bigger, the clock cycles as they propagate through will fall out of sync. Does that make sense? If I have a square wave and I'm sending it, and I send it over a short path and a long path, if they get to the same point by two different paths, they're not in sync anymore. And so there's only, even with all the money in the world, there's only so big we can make a processor. Because if we get bigger than that, now we have timing problems. Beyond that, the circuitry for faster memory is harder to build. Beyond that, registers can be faster because there's no addressing problem. Right? I have 16 registers. It's much easier to address. I don't need very many address lines, right? If I have way more memory, now I start to need a lot of address lines to address that memory. And now I need to be able to deal with that in terms of the circuit that addresses the memory. Does that make sense? So there's no one fundamental limit. We end up with a lot of limits. Limitations of real estate due to clock synchronization issues, due to the ability to fab things that are larger, blah, blah, blah. The complexity of the circuits, and the ability to deal with something larger when it comes to addressing the three that come to my mind offhand. There are probably more. If you take enough Comp E classes, you'll know more than me. Yeah?
On the DRAM, the refreshing, how does it go about refreshing? Because I get, if they're all ones, you can just shoot voltage along all of them, you recharge the capacitor. But how is it going to know to recharge the ones and not put any charges in zeros?
So how does it know, so what does the refresh circuit look like in DRAM? You know, that's a question I could have answered for you, but you would need the 20-year-old version of me. Okay. That knowledge has long been forgotten. And so sorry, I really don't remember what the refresh on the DRAM circuit looks like. But you can Google it because it is very well known. It's something that if you take an ECE course that deals with memory systems, you'll learn how to design that circuit and do that. Once upon a time I did, it wasn't my thing. And so it was one of those things I crammed in my head for an exam and forgot ever since. And so you shouldn't cram for exams, because had I studied properly, I would now be able to answer your question. This is why cramming is bad. Yes?
The memory controller reads the value, compares it to some clock level, and then if it's above the threshold, then it reads it as a 1. If it's below the threshold, then it reads it as a 0.
Right. So we certainly can imagine that it walks linearly through memory and does a refresh by reading and rewriting. I just don't know that that's actually what it does. Maybe you do, but I think it's actually more involved than that. Because DRAM is a collection of cells, and there's a buffer to access it, and I don't think it actually pollutes the row buffer when it does the refresh. But I would have to check.
If you're interested, take recording.
Okay. So your hypothesis is that it does what? No, go ahead.
It's supposed to go through every single horizontal row and then access the specific cell, and then compares it to some threshold voltage, and then if it's above the threshold, then it declares that to 1. So then when it gets the instruction to refresh it, then it puts back in the VDD. Otherwise, it just leaves it grounded.
But is that done by the memory controller outside of the row buffer, or a memory control, or a DRAM controller inside the row buffer, inside the DRAM cell? So the memory controller walks through all of DRAM linearly. If I have 64 megs of system in my thing, every 10 to 100 milliseconds, it's linearly walking through all of my memory. I don't know.
The entire system linearly. It can access different blocks simultaneously. It just can't access multiple parts of the same block at the same time.
Correct. So somehow this is not walking through all memory. The memory controller outside of all my DRAM is not refreshing all of my DRAM. This has to be done on the DRAM itself. Again, it's been literally you need the 20-year-old version of me, but the 40-year-old version of me says this is not happening on the system memory controller because it's not going to walk linearly through all of memory. It's got to be happening on those. Yeah, the DRAM chip itself has its own circuit, which is where I think the refresh is happening.
Yeah, I was talking about that memory controller, not the.
Okay, so if you're right, so it may well be happening on a DRAM and a refresh circuit on a DRAM. That's the more likely place for it to happen. All right. So anyway, DRAM does have this, DRAM does have this property that requires a refresh. Generally, the circuitry is a little slower. And so what we find if we look at how our memory is organized is that we have small amounts of SRAM used as cache, okay, on the processor itself, off the processor. And then we have our system's main memory is composed of DRAM. And then beneath that, underneath, we see that we have things like SSD or disk as storage underneath, forming our memory hierarchy. And we'll talk a little more about that. DRAM is traditionally packaged as a chip. The basic storage unit is called a cell. There's 1 bit per cell. And then to access it, this is the picture we want. Okay. Here we have a 16 by 8 DRAM chip. If you notice, it's 4 by 4 or 16, right? And so what do we see? If we take a look at this, what we have are rows and columns. And so what happens is we have a row access strobe or RAS and a column access strobe or CAS. Okay? The row access strobe happens first. And that provides a row address to the memory control, to the DRAM cell. And that causes the row to get copied to a row buffer. Okay? Now that the row is on the row buffer, we do a column access strobe and indicate the column we want and get the column out of the buffer. Does that make sense? Two separate operations. Row access strobe, RAS, to get the row, and then a column access strobe, or CAS, to get the column we want out of the row. Boom. This turns out to be interesting, actually, because that means that there's actually spatial locality within DRAM access. And that's something that a lot of people don't think about. If I access things sequentially within a particular row, I don't need to wait for that row to get copied to the buffer. Okay? So there we see the RAS copied to the buffer. Now we see the CAS. We get the one we want. And then you see how these things are all stacked up. We have cells just like the one we saw in that prior picture that form our individual DRAM modules. Those get stacked up to form our system memory. And then the memory controller's job is when we give it a particular address, okay, is to store that stuff across all of DRAM. It's important to notice that when we provide a particular address and say store this word, okay, that 64-bit 8-byte word is stored spread out across a whole bunch of DRAM modules, because that lets it happen in parallel. We don't have to write byte, 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 right, 8 times. Instead, we write the 8 bytes in parallel to 8 different DRAM modules. Make sense? And the memory controller handles that for us. There are all sorts of types of DRAM. I mean, the basic idea of DRAM hasn't changed since the 1970s. The slide claims it was invented in 1966. I'll believe it. The bottom line is that DRAM has been used in computer systems since the 70s. And the basics of DRAM really hasn't changed. We have had some enhancements to it over time, but basically DRAM is DRAM is DRAM. There's so-called SDRAM, which is synchronous DRAM. It allows the reuse of row addresses. So, for example, as Ro was talking about, where you can do a RAS, a row access strobe, followed by several CASs, without needing to do row access, column access, row access, column access, row access, column access. Right? As long as it knows that the memory controller knows it's accessing from the same row, it can just go straight across. There's so-called DDR SRAM, double data rate. It basically can access it twice per clock cycle. DDR2, DDR4, basically more bits per access. DRAM is much slower. A DRAM chip has an access time of 30 to 50 nanoseconds. And transferring it from main memory into a register can take 3 times or more longer than that. So in other words, it might take me 30 to 50 nanoseconds to read the DRAM, and it might take me another, 100 nanoseconds to copy it out. Very slow. If we compare this, if we take a look at this in terms of how this compares to CPU clock cycles, we can see in 1980, the slide here claims that the clocks were cycled at 1 megahertz. 1 megahertz. Not gigahertz, megahertz. Now, my memory back from 1980 is they were actually at 4.77 megahertz then, but I was like this big, and so I could be off. But a small few megahertz in the early 80s, right? By 1990, clock rates were at 20 megahertz. 1995, 150 megahertz. 2000, 600 megahertz. 2003, whoa! That was a really nice upgrade, by the way, for my 3-year upgrade there. 3.3 gigahertz. Oh shit, hide that slide, it must be wrong. What happened there? Yeah?
Because you can increase your clock cycle all you want, but if your architecture is bad, your CPU will still be slow. So they decide to improve the architecture, reduce power, because these CPUs were getting really, really hot, and it would melt if you kept going higher. And they decided to work on improving architecture and probably multi-core performance, and they reduce the clock cycle while still being faster.
Yeah, it's a pretty good summary. I mean, there's a material science problem. A lot of people think of Intel and AMD and so on and so forth as computer architecture companies. And to some extent they are. But they're also amazing material science and engineering companies. Because the architectures that computer engineers envision, right, actually have to be implemented on a chip. And what happened is, you've heard about Moore's law, that, something along the lines of every 2 years, the number of transistors or the speed or something like that doubles. No one knows exactly what Moore's law is, but somewhere in that ballpark. That basically there's this extremely rapid growth, right, fueled by miniaturization. And for years, people were predicting an end to Moore's law, that there's only so small we can make it. And that beyond that point, we simply won't be able to manufacture things any denser. And everybody predicted, that's it, this is the last generation, it's not going to be able to do this anymore. And somehow, magically, to everybody's surprise, the material engineers at Intel found a way. And somehow, the next generation of chip did it. And Intel got into the habit of predicting. Like, whatever people say, we're somehow going to be able to build this, because this is what our curve tells us. And eventually, they actually missed. They actually couldn't do it anymore. And they simply could not economically build chips, with any reasonable yield that were as fast as they'd hoped. AMD had actually given up this cause a little earlier, and had developed their own architecture. They basically said, look, if we can't get faster by being faster, we're going to get faster by parallelizing. Okay, we're going to have more cores. Because the average workload, unlike the workload in 1980, right, the average computer has a lot going on, just number of processes. And then in scientific applications, people really care about performance, they'll rewrite the code to take care of to make use of the multiple cores. And when Intel tripped, they actually put out a pretty bad processor there for a bit, where they basically took a whole bunch of existing processors and slammed them on the same core. But then they refreshed and recycled and came around with a new processor that was like AMD's, purpose-built for the task. And so now, we saw for a while that the way processors were getting performance was by more cores. Dual cores, 4 cores, 8 cores, 12 cores, right, 16 cores, and so on. And now what you've seen since that time, right, clock cycles are going back up again. Anybody bought a computer recently? What was the clock cycle on it? Speed?
3.3.
3.3? Anybody else?
Double boost more to 3.7.
Yeah.
Well, like Intel's current highest end desktop processor, the quad core model starts at 4 gigahertz, so it's pretty good.
AMD has a
Okay, so I mean, if you look at common systems, you're probably looking at the bottom being about 3.3, 3.5, pushing to 3.8, 4.0. I didn't know there was a 5.0 out there, but if you tell me, I'll believe you. And so, we really did see, that things were moving extremely rapidly, and then they actually reversed course, and now are moving forward much more slowly. So the bottom line here is, as compared to those processor speeds, right, DRAM is slow. It can take hundreds of cycles per memory access. And the speed of memory is not growing nearly as fast as the speed of processors. And it's important to realize from this perspective, we care both about parallelization and clock speed. Right? If we're executing the same instruction set, right, with the same number of cycles per instruction, and we have a higher clock rate, we're generating more memory pressure, right? Because we're doing more work per unit time. We're running through our program faster. So it's easy to see that as clock rate goes up, right, holding everything else constant, we're generating more memory pressure per unit time. As we get more cores, we're doing more work in parallel. Each core is now accessing memory. So it doesn't matter if we're getting performance by increasing clock speed or getting performance by parallelizing the CPU, we're generating more memory pressure. And memory is really not scaling at that speed. Right? When they went from 1 core to 2 cores, right, memory didn't get twice as fast. When the average system went from went to 12 cores, memory didn't get 12 times as fast as it was 5 years earlier. It'd be nice, but didn't happen. So we're seeing more and more memory pressure than we ever have. So performance of the memory hierarchy, right, is critically important. Approximately 1/3 of instructions are loads or stores. Here's a little picture showing the gap. Right? DRAM, SRAM, CPU. Rolling back to my day, okay, at least the first computers I ever used, memory and processor ran about the same speed. That didn't last long. I didn't make it out of elementary school before that changed. Okay? Now we're looking at this, we're seeing, access times, over here, processor times over here, and that's really not changing. Do you see that? And yet we're generating more and more pressure, even as this moves slowly in terms of downward, we're generating more and more pressure because we're multiplying the number of CPUs. Memory is under dramatic attack. But that's okay. Okay. If we think about how programs work, there is this concept of a working set. Okay? The things the program is using right now. If I wander through the collaborative commons at night, or one of the computer labs at night, or down by the cafe area, the library, and I look at students working, it's going to take me about 3.5 seconds to determine what you're working on. How?
Where you're sitting?
Maybe where you're sitting, but maybe something more obvious. What's that? What's that? I mean, it's definitely true that when I see people really excited and thrilled, I know they're working on 213.
There's a guy who's in a nervous breakdown because his computer was being stupid yesterday and he was doing 213.
So there's a guy who was really excited doing 213. I gotcha. Okay, so, but let's say I showed up from Mars and I was wandering around these spaces. How would I know what people were working on? What's the obvious thing? Yeah, look at them, right? I'd look and see, okay, there's the 213 textbook, right? There's Buff Lab. That person's working on 213. This person has, 2 books and a journal, two books and a literary journal in front of them. They must be somebody's significant other, right? Doing their literature homework. So you can look at somebody's thing. You see, look at the screen. You see, somebody sitting down with the Intel reference manual, right, and C code on the screen, right? What are they probably working on? Probably OS, right? So the bottom line is whatever task we're working on, there's a set of resources we need to accomplish that task. If you're working on 213, you may have your textbook, right? You may have your code out. You may have some web page with an assembly reference on the screen. That's the set of resources you need to do 213. Right? If you're doing 112, you might find some Python code on the screen, right? Some Python references, right? And a library reference or something, right? So when we're working on a particular task, there are a set of resources we need for that task. Have you ever tried to do work like on a plane? What's the problem doing work on a plane? It's cramped, right? You need to have your laptop, a book, and physical, like a notebook paper, right, to do an assignment. And yet you have this much. Okay, let's be real. You need your coffee, right? Or your soda, right? And your laptop, and your book, and your paper on the desk. And there's not enough space. So now you find yourself using your lap. Right? Putting something on your lap, doing this whole shuffle thing, right? That's not fun, is it? That's not really very efficient, is it? It's sort of like trying to program in one of these seats. The problem there is that we don't have enough space for our working set. We need 3 things to do our job, and we can only have 1 or 2 of them on the table, so we have to keep swapping. Does that make sense? Programs that have the same thing. If you look at what a program is doing right now, whatever task it's trying to accomplish, there are probably a set of variables, right, that it's working on. There's probably a chunk of code that's working on those variables. That's the working set of that process. Things are very, very efficient if that working set is in fast memory. Things are inefficient if that working set can't be kept in fast memory. It doesn't really matter at this point in time what else is in fast memory or isn't. What matters is that my working set is. So the basic idea for a program, right, for a system, is much like your idea when you're trying to get it set up to work, is to get onto the desk, to get into the processor, the working set, so that you can use it for a while. And then when you change tasks, change working sets. But the problem for the processor, right, is that it doesn't actually know what you're working on. It can't say, okay, this person's working on, generating some statistics based upon this set of numbers. I need to have this set of numbers in memory. It doesn't have a high-level understanding of what you're doing. So it needs to approximate what you're doing based upon some simple rules. And the rules that it used are based upon what's called locality. And in particular, 2 types of locality. Temporal locality, meaning locality in time, and spatial locality, meaning locality in space. Illicit electronically mediated communication. You're busted. Okay. So we have spatial and temporal locality. Spatial meaning near each other in space, temporal meaning near each other in time, right? Spatial locality, local, close, space. Temporal locality, local or close in time. So here's the idea. If I'm walking my way through an array, okay, and I access element 0, and then I access element 1, then I access element 2, and I access element 3, and I access element 4, I access element 5, what element do you think I'm going to access next? 6. That's an example of you using spatial locality. I'm going to access element 6 because it's nearby element 5. Does that make sense? Okay. Now let's say in the last 5 minutes I've used 3 items. I spun around this loop and used these same 3 local variables over and over and over again. Okay? And now I ask you, what variables am I most likely to use next iteration of this loop? Those 3. That's an example of temporal locality. I'm likely to use them again because I've used them recently. Right? There's the old adage that the recent past is a good indicator of the near future, right? If you want to know what's going to happen next, what's happened recently? If the stock market went up 5 minutes ago, it's likely to go up in the next 5 minutes, right? If it began to crash 5 minutes ago, maybe it's not a good time to invest. Of course, your returns may vary. So in systems, we very, very, very heavily leverage these two ideas. That the recent past is a good indicator of the near future, and that we're likely to access things near those that we've accessed before. Spatial and temporal locality. And we use spatial and temporal locality to estimate the working set. Does that make sense? To estimate the things we need right now. We don't have a high-level understanding to tell us what we need, so we use spatial and temporal locality to help us estimate. Okay? Crow-Brins tend to use data and instructions with addresses near or equal to those they've recently used. Okay? Temporal locality, recently referenced. Spatial locality, nearby those referenced. So if we take a look at a loop, okay? I equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? As we walk through array A of I, that's an example of spatial locality. Okay, temporal locality, for example, occurs with respect to the instructions themselves. Okay? Those instructions are located near each other, right? Spatial locality. There's also some temporal locality because we're going to access them close in time, and that's going to help us, for example, this variable called sum may be at a different place than these instructions, right? They're not near each other in memory. This variable sum, depending upon where this is in the data area or the heap, right? The stack maybe, whether it's a local or global, right? This is down in the text area. They're not nearby. There's no spatial locality when we look at code and variables, right? But there is temporal locality. I'm using them together in time. Okay? So being able to look at code and get a qualitative sense of locality is a key skill for professional programmers. There are two things that come to mind when I think about performance. Okay? One is that human intuition is a really poor way of estimating system performance. The second is that you can't even get to decent performance without good intuition. And so what we need to be able to do is use good intuition on our first pass to do things in a way that makes sense. And then be able to profile and analyze our systems using tools to be able to tune it the rest of the way. And so if I look at code like this, I see that I have some array called A. Now, when I have a two-dimensional array, dimensions m and n here, right? How is that array placed into memory? Row major order. In other words, rows are kept intact, right? But columns ended up separated. So if I'm walking across a row, do you see that's good for spatial locality? I access something in a row, and I access the next thing in the row, it's right there. If I go from column to column to down a column, right? From row to row to row, but down a column, I end up in a situation where I skip from row 0 to row 1, to row 2, to row 3, to row 4, to row 5. Is that good for spatial locality? No. Okay. And so if we take a look at this, we see that I have two loops. One iterating on I, one iterating on j. Row access is here, column access is here. So if we look at this, we see that I'm accessing row 0, column 0, 1, 2, 3, 4, 5. Row 1, column 1, 2, 3, 4, 5. Row 2, column 1, 2, 3, 4, 5. I'm walking across a column, and not until I'm done walking across a column am I moving to another row. So I have good spatial locality there, right? I'm walking across an entire row before I skip columns, and even then, my rows are back to back. But if I make a simple change and reverse these indices, or reverse these indexes, right? IJ now became JI. Now what's happening is I'm moving from column to column to column. Nink, 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 nink. Do you see how that blew my spatial locality? Simple, tiny little change could make a big difference. And the really funny thing about it is that if you try this on a small example, you might not notice. Because your block size might be big enough that you're walking within the same block. But on a bigger example, where your array starts to grow, now it'll start to really, really hurt. Okay? We can stack it up 3 deep, and the same thing is true. Right? We want a situation where our innermost index for the for loop is our outermost index of the array. So ijk, kij. Not ideal there. Okay? Now, let's talk about specifically how it is that the system actually makes use of this. Okay? We've talked before about the memory hierarchy, the pyramid, right? That at the top we have the registers that are really fast, the same speed as the processor. Then we have our SRAM, our cache, some of which is on board the processor, some of which may be on on the motherboard itself, right? And then we have the DRAM. If we think about it, we have the registers, probably some SRAM cache on each core, probably some SRAM cache on the processor, right? And then these days, probably not as much on the motherboard. We just jump right to DRAM there. Okay? And then after the DRAM, maybe we have an SSD drive or an SSD layer on top of our magnetic hard drive. So we actually go registers, SRAM, DRAM, solid state device, disk, network storage. Okay? The stuff at the top is really expensive, right? Processors are made out of expensive stuff, right? The stuff at the bottom is really cheap, disk. Right? Your price per gigabit of disk is really, really, really low compared to your price per gigabit of RAM. So the goal is to keep our working set as high up as possible, right? In the registers if possible. And if not in the registers, at least in the SRAM cache. We want a situation where we move it up the hierarchy, and we pay a price for that, but we use it there for a really long time, amortizing that cost and the cost of writing it back. Okay. The way this is done is with something called a cache. And the idea is that we have a small amount of fast memory caching a larger amount of memory. There's more stuff in memory than there is the cache. The cache is only holding the small stuff. Hopefully, small stuff that we need right now. Okay? So stuff is copied from memory into cache. We use it out of cache, and then eventually we write it back to memory. That means that it might be possible, right, depending upon the cache's organization, for us to have a value in cache that's not in main memory. It's been updated. Okay? So if I have a small amount of stuff in cache and a larger amount of stuff in main memory, it's possible that I'm going to access memory that's not in my cache, right? Not everything is cached. We call that situation a miss, a cache miss. If we try to find something in our cache and it's there, we call that a cache hit. Cache hits are much better than cache misses because we deliver it at the speed of the SRAM cache, not the speed of the DRAM memory. Okay? All right. I think we've talked about that. So if we look at the sort of the hierarchy here, we see that CPU and the registers on it, right, are faster than SRAM, which is faster than DRAM. We have SSD, and SSD has actually gotten a lot faster since the slide, disproportionately faster. SSD and disk. We see that disk really hasn't gotten a lot faster. At the end of the day, a disk is a mechanical system. Parts actually move. Okay? There's actually inertia. You have to start and stop things. Wait for them to get stable, right? Disk is slow. SSD is a great technology. It used to be that it was much slower to write to SSD than read. And if you've looked at recent SSDs, that's gotten a lot better. DRAM, SRAM, CPU. And so this forms our memory hierarchy. As it turns out, registers are the most expensive but the fastest, followed by SRAM, followed by DRAM, followed by SSD, followed by disk. As we go up this, right, these things get slower, but they get cheaper. As we come down, they get faster and more expensive. So DRAM, right, costs about 100 times as much as SRAM. I'm sorry, SRAM costs about 100 times as much as DRAM, right? But it's about 10 times faster. Okay. Here's the picture of the pyramid. We showed it to you the first day. Mentioned it a couple times since. Registers, L1 cache, L2 cache, main memory, secondary storage, remote storage. Registers, right, SRAM, SRAM, DRAM, local disk, remote storage over a network. The idea here is the memory hierarchy creates a large pool of storage that costs as much as the cheap storage near the bottom, but serves the data to the programs that are ready to the fast storage near the top. That's a wonderful idea, isn't it? You get the performance of the fastest memory for the price of the slowest memory. What enables us to do this? This idea of a working set. This idea of spatial and temporal locality. The fact that we can take what we need, move it up that hierarchy, and use it for a long time, paying the price that it costs to get us there. So we can amortize that cost, making it essentially go away. Does that make sense? If we didn't have a good working set, if we weren't able to find it using spatial and temporal locality, then we wouldn't be able to amortize that cost. We'd pay the price, bring it up, pay the price, bring it down, and we wouldn't be able to amortize it across a lot of operations. So we'd be operating at the speed of our slowest storage. Okay. When we talk about misses, there are three types of misses. Compulsory misses, conflict misses, and capacity misses. So let's talk about what they are. When I turn the system on, is there anything in my cache? No. Okay, if there's nothing in my cache, is it possible to have a cache hit? Oh. I was coming to get him, and you woke him up? I think you have a friend.
Yeah.
She saves you, you know that, right?
Yeah, I know.
Anybody else sleeping?
Yes.
Where? Where? Let's see if we, oh. Ah! All right. I don't know about you, but I'm now awake. Okay. So, where were we? So if I turn the system on, okay, we've said there's nothing in the cache, right? It just got turned on. The memory's empty. Is it possible for me to have a cache hit when the cache is empty? No. Is there anything at all I can do about that? No. That's why we call it a compulsory miss. It's compulsory. There's nothing at all we can do about it. Make sense? Sometimes we call it a cold miss, because the reason the miss is compulsory is the cache is cold. It's not warmed up yet. It doesn't have stuff in it yet. Does that make sense? Okay. A capacity miss occurs when the size of the working set is bigger than the size of memory. Okay, this is the situation where you're trying to do work on an airplane. Okay, or you're trying to do significant work here, right? Your table is like this big. Is there any way you can efficiently handle your laptop, your books and your coffee on a table this big? No. At the end of the day, right, you're going to be inefficient because there's just not enough space. No management technique is going to solve that problem. If my program's working set is larger than my cache, right, my cache simply doesn't have enough capacity. Does that make sense? I have a capacity miss. Okay. Now, we understand cold misses. We understand capacity misses. Now let's talk about conflict misses. The conflict miss occurs when our cache size is greater than or equal to the size of our working set. So it is possible to keep our working set in cache. But because of the decisions we've made, because of the way our cache is organized, we have misses anyway. Does that make sense? That's why we call it a conflict miss. It's conflicts between what we have in the cache and what we need to have in the cache that results in the misses, not the size of the cache, not the fact the cache hasn't warmed up yet. Does that make sense? So I know that I have a compulsory miss if I just turn the system on, the cache doesn't have stuff yet. I know that I have capacity misses if my working set size exceeds my cache size. I know that I have conflict misses if my cache size is bigger than my working set size, yet I miss because I have the wrong things in the cache. Because my simple rules, like using spatial and temporal locality, mispredicted the working set. At least the way I use those rules mispredicted the working set. And so here are examples of caches in the hierarchy, right? Caches are used all over. Registers are a type of cache, right? The TLB translates page addresses. We'll talk about that. L1 and L2 cache. The buffer cache for disk, for files. Network caches, browser caches, so on. So the summary here is that there exists a speed gap between CPU and between memory and mass storage like disks. And it continues to widen because the CPUs are getting faster and faster and faster. And remember, the slides don't emphasize this enough. They're getting faster and faster and faster, both in terms of clock speed and in terms of the number of them. Having more cores generates more memory pressure. They don't have to be faster, right? But well-written programs exhibit this property called locality. They have spatial and temporal locality. We can find the working set, the things they need right now, because they've used them recently or they're nearby. And memory hierarchies take advantage of this to keep the stuff they need higher up, saving things they don't need in the lower layers for later. This allows all the work to happen at high speeds, while all the things that will happen in the future to be stored safely at a lower cost. Make sense? Okay. What's inside a disk drive? Who cares? My entire lifetime, people have been predicting that it's going to be the end of the disk drive, because they're clunky mechanical systems. And for a while I believed them, and then I didn't because they were never to be believed. And now I believe them again. Because SSD storage is amazing, right? It is actually going to put an end to disks, I think. The only thing I want you to get from this, right, is that these are actually mechanical systems. The disk actually has to spin. The heads actually have to move. This takes time, okay? These heads that actually have to move, right, they're stopped. The disk is spinning under them, okay? Now I have to energize that motor and swing that disk head. I have to get past the moment of inertia, get that disk head moving, and now I have to stop above where I want to stop. Hit the brakes. And now that I stop, there's a natural tendency toward oscillation, right? Any mechanical engineers in here? Mech? Okay. Right? This is a tough problem. Right now I have to wait for that oscillation to dampen out to the point that it's actually sufficiently above what I want to read for me to read it. Doing the wave back there, I gotcha. Okay? That's slow. Now they build in memory, they build in, cache on drives, right? Used to be they build in DRAM cache on drives. Now some of the drives actually have an SSD layer too. But they're clunky mechanical systems. The disk spins at a constant speed. The heads stay in place, and it forms these things called tracks. Track is the path underneath the head. Okay? If you look at it and look across all of your heads, because the heads stay together on an arm, you see what forms a cylinder. Head 0, head 1, head 2, head 3, head 4, and so on. And that's the set of tracks that are underneath the cylinders. It used to be, and you can imagine why, that if you had to write, you would do a big write. You'd write to track 0, and then you'd write to track 1, and then you'd write to track 2, and then you'd write to track 3, and then you'd write to track 4, and so on. Because you wouldn't have to move the head to do that. Does that make sense? And so that would be faster. The head switch delay was faster than a seek delay. These days it's not really clear. Because things have gotten so dense that the heads themselves are not perfectly aligned to the media. And so when you switch heads, you could end up having to recalibrate anyway. Maybe not mechanically, maybe just the DSP, but there's a lot of work that still needs to be done. And so a head switch delay these days is not trivial. But if you want to take a look at some parameters of disks, vendors generally express capacity in terms of gigabytes. The recording density can be talked about in terms of bits per inch. Okay, so that's if we follow along one of these tracks, how many bits we can write per inch of track. You can talk about track density, number of tracks per inch. Okay, you can talk about the so-called areal density, which is, forget about the tracks for a minute, just how many bits per square inch of disk. Okay. Back in the day, the innermost track, which was, by the way, the smallest, and the outermost track, which was, by the way, the largest, stored the same amount of information. The reason for this is that from the perspective of the disk head, they look the same. Because the disk is spinning at the same RPM. So it's one rotation of the inside, or it's one rotation of the outside. And if the disk is spinning at 3,600 RPM, the waveform underneath the head looks exactly the same. And where the electronics were at the time, they just couldn't differentiate that. So the density of the disk was limited by the density of the inside. These days, the electronics have gotten much, 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 much better. The DSP is better. We can actually figure out where we are on the disk, right, and interpret the waveform better. And so now we have these things called zones. You can imagine an outer zone, a middle zone, and an inner zone. And we have more sectors per track. A sector being just a group of bytes that we write together. We have more sectors per track on the outside than on the inside. So if we're in the outside zone, we will have more bits per track than we will on the inside zone. Okay. So if you want to talk about capacity, if you take the bytes per sector, okay. If we take a track, again, we just divide that up into sectors. Sectors are the fundamental unit. You read or write an entire sector at a time. The bytes per sector times the average number of sectors per track. Why the average number of sectors per track? Well, on modern disks, the outside have more than inside, right? Because the outside zone, has more sectors per track than the inside zone. So they're saying here, just take the average. Take the bytes per sector, multiply it by the sectors per track, multiply it by the tracks per surface, multiply it by the number of surfaces per platter, multiply it by the number of platters, basically take all these things and multiply it out. And that'll give you the capacity of the disk. So if I have a disk that has 5 platters, right, each platter has 2 surfaces, that's 10 surfaces. If each surface has 1,000 tracks, that's 10,000 tracks. If the average track has 10,000 sectors, whatever that is, right, we can multiply it by there. And you can just turn around and multiply that out to get the total number of bytes per disk. This doesn't really work. This is very 1990s or 80s logic. The reason is that the drive manufacturers don't tell us anymore how many sectors per track or how many zones. They don't give us that level of specification. So there's nowhere, it used to be you could read on a sticker, this thing has 4 surfaces with X tracks per surface and blah sectors per track. That information is just not available anymore. Drives are very proprietary. It's too detailed because there are too many zones, things like that. So this math is all really a fiction. Okay. Okay. Here we see a picture of the disk just shown as a pie, where you have the tracks, the sectors per track, and then you access a particular sector. To access a sector, there are 3 types of delay you're going to get into, at least traditionally speaking. There's the rotational delay, while the disk spins. Okay? There's the seek delay while you move the arms, and the transfer delay while you would read the data. So you can imagine you seek first to move the arms to the right track, letting things stabilize. Okay? Then you wait for the disk to rotate so your data is underneath. Then you sit there and read your data until you have it. Seek latency, rotational latency, and then transfer latency while you read it. Okay. Okay. Seek, rotate, transfer. Okay. Seek times average 3 to 9 milliseconds. What's the difference? It's probably about 9 milliseconds, 8 to 10 milliseconds, doing what's called a full sweep seek from the inside to the outside. To bump from one track to a nearby track is actually very slow. It's not much faster than the full seek, because it still has to start and it still has to stop and still has to stabilize. So you might see a 10 millisecond, full stroke seek and a 3 millisecond track to track seek, even though you might have, many tracks. So you can talk about an average seek time, right, which is a little different than half of a full seek, right? Rotational latency, take your RPMs, right, invert it, right, RPMs rotation per minute, invert it to get minutes per rotation. Right? If you figure you need to rotate halfway around the average case, that'll tell you how long your average rotation is going to be, right? Average rotation is half a disk. If you have 3,600 RPM or 7,200 RPM or 10,000 RPM, invert the RPMs to give you minutes per rotation, convert the minutes to seconds, and go from there. Transfer time, well, figure out what percentage of rotation you're going to need to read. So if we have a 7,200 RPM disk with an average seek time of 9 milliseconds and an average number of 400 sectors per track, we can then figure out the average rotational time. The average rotation is half of a full rotation. So we take our 7,200 RPMs and we invert it, 1 over 7,200. That's 1, rotations per minute inverted is minutes per rotation. Multiply it by 60 seconds per minute. Multiply it by 1,000 milliseconds per second. And we end up with 4 milliseconds. So that's my average rotation, my half rotation. Now my average transfer time, it's going to be the same thing, right? 60 over 7,200 times 1 over 400. Where does that come from? That's my average number of sectors per track. So if I'm reading one sector, I'm reading 1/400th of that. So once I rotate in the average case, half a disk rotation to get where I want, if I'm reading one sector, I'm reading 1/400th of a rotation. So it's 1/2 plus 1/400th. And now I'll do the same thing by multiplying by 1,000 milliseconds per second to give me 0.02 milliseconds. Okay. Access time is going to be my 9 milliseconds for my seek, plus my 4 milliseconds to rotate, plus my 0.02 milliseconds to read. Okay, so the thing to note here is the access time is dominated by the seek and rotational latency. In other words, the actual reading of the data is the easy part. Getting to the data by seeking and waiting for it is what takes time. Okay. So SRAM access is about 4 nanoseconds per double word. DRAM access is about 60 nanoseconds. Disk is about 40,000 times slower than SRAM. It's about 2,500 times slower than DRAM. People pay a lot of attention sometimes to the number of cores and the number of the clock cycle of the CPU. People sometimes pay attention to caches. People oftentimes neglect the total amount of system memory. Right? One thing I've observed over time is that people will buy the fastest CPU they can buy. Maybe they'll buy the biggest core, the highest core count they can buy. They'll say, okay, I'm going to get the 8 core count, blah, blah, blah CPU. and then they'll take whatever amount of memory comes with the system. And I think the rationale is I can always add memory. But how many people have added memory to a system recently? Relatively few. Right? You can, but relatively few. Right? One of the things I learned is that when buying systems for the clusters on campus, right, I need to buy way more memory and less processor. Because if I have a whole bunch of people SSH'd in, what do they need? Memory. Right? If those systems end up swapping to disk, they get way slower really fast. It doesn't matter how fast the processor is. If my processor is, is a little bit slower, no big deal. But if I swap to disk a little bit more often, system performance completely falls apart. When you're dealing with heavy multi-programming, large data sets, more memory is really important. Yeah?
How much memory does one of those Shark machines have on it?
I don't remember offhand for the Shark machines. We've had those for a few years.
Well, whatever you've put in recently, how much memory do you guys think?
I usually look to throw in about 32, if I can. Some of them are as low as 12, but it's really memory is important. Logical disk blocks, I told you earlier, the geometry that we're talking about is now totally a lie. So they don't actually tell you what it is because A, it's too complicated, and B, it's proprietary. So instead we talk about logical blocks. Block 0, block 1, block 2, block 3, block 4, block 5, block 6. We don't worry about any geometry other than that. It's called logical block addressing. The assumption we can make that's generally true is that the greater the distance between logical blocks, the slower the access time. Does that make sense? If I'm accessing logical blocks that are very near each other, it's probably going to be relatively fast. If I'm accessing logical blocks that are farther away, it's probably going to be relatively slow. But we can't make any specific assumptions about when we're going to encounter head switch delays, or when we're going to encounter seek delays, or things like that. There's also all sorts of other things that happens. For example, there are some bad sectors when the disk is made, and those get mapped away, they get hidden. Picture of the bus again. This is just the picture we saw before, but with a few more things decorating it, right? We have our ALU, our register file, the system bus connecting us to our I/O bridge, connecting us to the I/O bus. There's a memory controller connecting us to the memory bus, some I/O controller connecting us to the I/O bus, and we have like a disk controller connecting us to the disk. Okay? Traditionally speaking, what actually happened is we made a request to the disk, okay, and said, disk, give me. Okay? And then what happened is we blocked whatever process was asking for that because it wasn't ready yet. And when the disk was done, it generated an interrupt. And then what happened is an interrupt handler fired off. The processor stopped what it was doing and went and got the data from the disk and copied it to memory, unblocked the process that was blocked, and then went back to what it was doing. So the main CPU was coordinating disk accesses. The main CPU was coordinating this communication between, the disk and memory. Okay? In modern systems, it doesn't work that way. Modern systems, the disk have what's called DMA, or direct memory access. Basically, the disks themselves have a processor that can function like the other processor and take control of the bus. So we'll go to the device and say, dear device, please read these bytes for me and put them in this buffer in memory. The device will then get the bytes off the disk, copy them into memory, and generate an interrupt when it's done. So the processor on the disk controller, the DMA controller, is coordinating the movement of the data from the disk to memory, not the processor. Does that make sense? This is good because it offloads work from the processor. It's bad in some nominal sense because it means two different processors are competing for the bus. And you can get some contention. where the main processor is trying to use the bus for one thing, but the DMA controller has it for another. But in general, it's a good thing, because it's offloading work from the CPU by adding a processor that can do that type of lightweight work. Okay? Solid-state devices. The bottom line there is that we have a whole bunch of individual blocks that are formed from flash memory. Okay? Things like NAND gates. Okay? From those, we need to present some type of usable file system, right? So the first layer is we build up some logical addressing. We go from having our flash storage to having block 0, block 1, block 2, block 3, block 4, block 5, block 6. Okay? Now, we could just address the memory directly and linearly, but flash has this characteristic that it can only be written a certain number of times. Okay, then it wears out. I think way too much is made of this property because it's like 100,000 times that it can be written. It's huge. But nonetheless, there are certain things that get written more often than others. Certain blocks may go bad. And so the flash translation layer provides an abstraction. It provides the mapping between our blocks that we understand, logical blocks, and the actual storage. And so it's able to do things like wear leveling. Like every time we write, swap in a different block so we don't keep using the same block over and over and over again. If one goes bad, replace it with another and hide that from us. Okay? That's called the flash translation layer. And so we have the flash memory and the flash translation layer together form some solid-state device. These can be small things like thumb drives or big things like SSD disks. They can be built in some cases, to other disks, where you have some high-performance disks that have mechanical disks with an SSD layer serving as a cache, all built into one package. So they come in all different forms. They're used in a lot of embedded devices, like your DVD player, things like that, Blu-ray player. Okay. This slide is outdated. It shows a fairly significant gap between random reads and random writes. Do you see that? That was the case just a few years ago. They've gotten a lot better. That gap has been significantly closed, and I think it'll probably get closed some more. Okay. But the reason that writes were initially slow is because you couldn't really update a flash memory. You had to zero the flash memory and then rewrite the whole thing. So any write involved first a read, then a write. Read to find out the old bits, merge in the changes, write out the new bits. And so it was read, erase, merge, write. And that was just a slower process. Okay. What are the advantages of SSD memory? Well, there are no moving parts, generally makes them more rugged. They're faster. They have the potential to wear out. I hate that. I got news for you. Mechanical disks wear out too. Right? I can tell you that I've seen more mechanical disks wear out than flash memory devices wear out. But that's mitigated by wear leveling logic and so on. The real disadvantage to SSD is what? Yeah, cha-ching! All sorts of applications. We love SSD around here. The new cluster systems, by the way, they have solid-state disks. They don't have mechanical disks. Storage trends, what do we know? Memory, access times, getting better, right? Costs getting lower. DRAM, same thing, right? Disk, not getting as much faster recently, right? But getting cheaper. Back to our pyramid, right? The goal here is by respecting the working sets, using spatial and temporal locality to approximate them, right? Keeping the things we need at the higher level, so we perform as if everything is in registers or L1 cache, but at an average cost much closer to having things in secondary storage. We've been through this. Okay. I think we had some extra slides there at the end. Any questions? Yeah. You guys stay steady through questions. Yeah.
Would something like the stack be put into cache?
Yeah, I mean, so the stack, the question is the stack put in cache? And the answer is yeah. I mean, the stack, the heap, the text area, these are all part of memory. They're all addressed. And so when we look for our working set, right, even though the stack may not be near the code may not be near the heap, if those things are being used together, hopefully through temporal locality, we'll discover that. We'll see they're used close in time, and we'll keep those in our cache. Does that make sense? Even though they're not spatially located together. And we'll talk about the details of how that cache works next class. Any questions? Have a great day, everybody. Oh, wait. Sorry. I'll come get yours.